The sodium channel consists of alpha and beta subunits. While the beta subunits play a role in localization, the alpha subunits, approximately 20,000 amino acids, make up this channel. The amino acid residues are organized into 4 homologous domains and 6 transmembrane units. These alpha subunits are encoded by 10 genes altogether, 4 of which are primarily found in the CNS, 3 in the PNS, 1 each in skeletal muscle and the heart. One specialized sodium channel protein is different because it is not voltage gated and is instead involved in salt sensing. In addition, the sodium channel also consists of 4 beta subunits, 2 of which are bound to alpha subunits through disulfide bonds. Looking at the sodium channel from above, we can observe a centrally located pore surrounded by 4 modules made of S5 and S6 segments and the pore loop. On the outer rim of the surrounding pore modules, there are S1 through S4 modules. S4 happens to be the voltage sensing, while S1 through S3 work together to hold the voltage sensing, the S4, in place. Now you know the general structure of the channel. Try to visualize putting this into a neuron at the resting membrane potential. To begin with, the pore is found in a closed state, which is located at point A on the action potential diagram. Basma will tell you more about this state.
In the closed state, at rest, a membrane potential of negative 70 millivolts exists, and 2-phenylalanine amino acid residues of segment 6 are found in the pore, which closes it to ion flow. This is due to the voltage sensing segment S4, which is sensitive to the membrane potential. At the resting membrane potential, segment 4 is shifted closer to the inside, helping the channel to close by moving segment 6. However, once the stimulus reaches the cell and depolarizes the membrane from negative 70 millivolts to negative 55 millivolts, the voltage-activated sodium channel opens. This allows many sodium ions to rush into the cell, depolarizing it even further, until it reaches around positive 30 millivolts.
Although we know that the initial depolarization causes the sodium channels to open, what molecularly causes the channel to open? Recall that the voltage sensor is located in the S4 segment. This S4 segment is a transmembrane segment in both the resting and activated states. This is crucial as it is able to sense the change in potential across a membrane. The S4 segments contain 4 to 8 repeated motifs of positively charged arginine residues, followed by 2 hydrophobic residues. These give the S4 segments an overall positive charge. At resting membrane potential, the positive charges of the S4 segments are stabilized in their transmembrane position by forming ion pairs with neighboring negatively charged residues. When the depolarizing stimulus increases the membrane potential to a threshold, usually around negative 55 millivolts, the positive S4 segment is repelled less by the positive exterior and attracted less to the negative cell, which causes an upward movement of the S4 segment. This S4 segment moves outward and rotates, transporting the gated charges from an inner water accessible vestibule to an outer water accessible vestibule. The X4 segment and its gating charges move through a narrow gating pore with short transit through the channel protein. This movement and rotation opens the pore that is made by the S5 and S6 segments and allows sodium ions to be conducted through the pore. The activation gate of the sodium channel actually remains in an open configuration until the neuron returns close to its resting membrane potential, which allows the S4 segment to shift downward again. However, sodium ion flow stops near the peak of an action potential around positive 30 millivolts, because shortly after the opening, an activation gate closes the pore from the inside, a step we will discuss after describing why the channel is permeable to only sodium ions.
Upon opening of the sodium channel, to prevent every type of ion to transport across, channels have ways to select which ions are allowed to cross. This is known as ion selectivity. The selectivity of the ion is due to the structure of the channel itself. At the extracellular end, there is a large vestibule followed by a narrow channel that is made up of glutamic acid residues. Glutamic acid has a negative charge attached to it that creates a pull from surrounding positive ions, such as sodium. The glutamic acid is the key determinant in ion selectivity. The glutamic acid creates a high field strength that attracts the surrounding sodium ions toward the channel. The sodium ions being pulled toward are bound to 4 water molecules, also known as its hydration shell. The negatively charged glutamic acid side chains interact with the water and partially dehydrates the sodium ion as it moves through the narrow portion of the pore, called the ion selectivity filter. After traveling through the channel, it rehydrates and a new ion is selected for. Drugs and anesthetics can block the selectivity of the filter by binding to the amino acids at the extracellular end of the channel. The channel is only selecting for negative ions when it is in the active state. After a short while, the channel becomes inactive and is no longer transporting ions across the membrane. You may be asking yourself, how does this happen? Next, we will be taking a closer look at the inactivation gate of the sodium channel.
First, going back to the general structure of the sodium channel, I would like to emphasize that the pore of the voltage-gated sodium channel is formed by the connection of 4 protein domains, each with 6 transmembrane segments. Each domain is connected by a loop. The loop that connects the 3rd and 4th domain, specifically the S6 segment from domain 3 to the S1 segment from domain 4, forms the inactivation gate. It is a peptide chain of about 53 amino acid residues. When the loop bends into the mouth of the pore, inactivation is complete and sodium ions do not flow. The whole inactivation gate is formed by the supersecondary alpha helix with 3 critical amino acids, the IMF motif, representing isoleucine, methionine, and phenylalanine, near the middle of the looped helix. The integral hydrophobic residues of the IMF motif need to interact with the complementary hydrophobic residues, usually glycine, on the receptor in the pore. While the IMF motif is the major structure involved with the folding of the loop, other amino acids within the helix indirectly control the inactivation gate through regulation. The hydrophobic residues of the IMF motif, isoleucine, methionine, and phenylalanine, are essential for stabilizing the folding structure. Previous studies have shown when the phenylalanine is removed from the motif, the inactivation gate no longer folds, and inactivation in general is hampered. Nearby polar residues such as threonine and the negatively charged glutamate have been identified in other studies to also aid in folding, suggesting that folding is not solely due to hydrophobicity. A serine residue near the C-terminal portion of the alpha helix can be phosphorylated by protein kinases to slow down the inactivation gate. Many studies have shown that the inactivation gate may not have voltage sensing capabilities like the activation gate. Rather, the inactivation gate simply follows the lead of the activation gate, such that the IMF motif of the inactivation particle becomes available only when the activation gate is activated and changes its conformation into an open state. The importance of the structural basis of the inactivation gate cannot be understated. Its mechanism is important for stopping ion flow at the peak of an action potential and allowing potassium ions to move the potential back to resting levels. Inactivation also creates a refractory period for the cell, thus preventing the breakdown of gradients and cell depth.
Now that we are at the top of the action potential at around plus 30 millivolts, what causes the membrane potential to fall back to its resting potential? Well, the voltage-gated potassium channels are responsible for the falling phase seen here. These potassium channels are also sensitive to the depolarization in the membrane potential. However, the potassium channel gates take a longer time to open compared to the sodium channels. The peak ion permeability also occurs later than sodium ion permeability as shown on the graph. As a result, the potassium channel opens when the sodium channel has already been inactivated and the membrane potential is at plus 30 millivolts. The electrochemical gradient of potassium favors the efflux of potassium ions, which causes the membrane potential to become more negative. This is referred to as repolarization. As the potassium ions continue to move out of the cell past the resting potential of negative 70 millivolts, the membrane potential hyperpolarizes to negative 90 millivolts before the potassium channel closes. Because the sodium channels in the cells are leaky, some sodium ions are still brought inward, raising the membrane potential back to its resting value of negative 70 millivolts.
When the membrane is repolarized below negative 55 millivolts, the sodium channel closes once again, waiting for another action potential, before it reopens and begins the process all over again.